Hi everyone. This is going to be our lesson on solving equations involving logarithms and exponential functions. So we will work about halfway down on page 7 in our Unit 3 notes. We'll start right at this heading here, solving exponential equations using logarithms. So what we're going to do as for this particular note video is we're going to talk about a few different ways to solve equations. Right, so a lot of the familiar moves we have, right, using inverse operations will come back, but just our inverses are maybe a little different than what we're used to. So let me read through the top text here. In the case that we cannot solve a function using similar bases, we are required to apply logarithms as a way to isolate the variable out of the exponential position. I think about this as unlocking that exponent. This requires taking the logarithm of both sides to use the power property, and we will solve from there. So the way we want to approach this, A is actually set up, this is what we're trying to create. We want to create a situation where we can rewrite in logarithmic form, right? We want to rewrite in log form. So what we'll do here is we're going to just directly make a transformation here. We're going to write this as, we're basically taking the log base 2 of both sides. Now what happens on the left is we end up asking 2 to what power is 2 to the x? Well, that's just x, right? We're just left with the exponent x. Now over on the right, if we didn't have our calculator, log base 2 of 10 is a perfectly legitimate answer, but we can use our calculator either using the math feature and using the change of base or using the change of base formula to find that the decimal equivalent of this answer would be 3.321. So what does that answer actually represent? It tells us that if we were to raise 2 to that number as an exponent, the result would be 10. So rewriting in log form or taking the log of both sides is certainly what we want to do on part A. If we slide over to part B, we have another equation here. This one's got a little bit more going on. So first, we are going to take an extra step here to isolate the exponential term. So what do I mean by that? Well, I'm going to subtract 6 from both sides, just like we would solving any other equation. Now I have 5 raised to the x plus 2 equals 860. Well, now what we've done is we've effectively turned problem B into a problem just like problem A. Now we can take the log of both sides. So what we're going to do as our next step is we're going to take the log base 5 of 5 to the x plus 2, and we're going to do that to the same, we're going to do the same thing to the right side of our equation. So on the left, what will happen is that because this log base and this exponent base are the same, these cancel, and we're left with x plus 2. And over on the right, here, we would assume this to be a calculator problem. We can use the change of base formula to find that log base 5 of 860 is actually 4.198. Now, just as like a sanity check, I think it's always worthwhile to just make sure your answer makes sense. We know that 5 to the third is 125. We know that 5 to the fourth is 625. So this answer does make sense. It's a little bit more than 4, and 860 is more than 625. As a final step, we're going to subtract 2 from both sides to solve for our variable, and our answer will be 2.198. So in this case, we had to take an extra step. We had to isolate the exponential, and then as a final step, we had x plus 2. Well, that doesn't change much. We just subtract 2 from our answer. All right, let's look at a couple more. Here, we are going to try to think about what could go wrong. So we will start again by approaching this the same way. I want to deal with this -7 being multiplied, so I divide. I get 1 over 4 to the x power equals -10. And I can continue as I would say log base 1/4 of negative 10 equals, oh, sorry, I had that, I'm jumping a step here. 1/4 to the x, and that's going to equal log of 1/4, log base 1/4, excuse me, of negative 10. So we get to the point where we say x equals log to the 1/4 base of negative 10. And this is one of those situations where we got to recognize a red flag, right? There's something that doesn't quite smell right here. And the idea is we have a domain issue, right? We can see here that we're trying to make a positive number, 1/4, right? 1/4 raised to what power equals 10. Our calculator is going to give us a domain error because it is impossible to change the sign of a number using exponents. So this example C is a situation where we have no solution. Why do we have no solution? Because we can never, ever, ever take the log of a negative number. All right, one last problem here. Now we have a couple of exponential terms, and in this case, like we saw earlier in the unit, we're benefited by combining these. So what would I do here? Well, I would write this as 5 to the x times 5 squared to the x equals 3. And this allows us to combine into a single exponential. As you can see here, we add the exponents. X plus 2x is 3x. And again, we've created this situation. We're taking the log, in this case, base 5, of both sides will get us to something like an answer. So over on the left, again, the log base 5 and the 5 cancel. I'm just going to move us up here. We'll have 3x, and that will equal log base 5 of 3. That is a decimal approximation of 0.682. That's 3x, so we divide both sides by 3 to solve for our variable, and we find that x equals 0.228. You may notice in this unit, I'm rounding to an extra decimal, right? 3 decimal places is a good idea for exponential terms just because exponents have a pretty significant effect with just small changes to their quantity. So we will round to an extra decimal place. All right, really quickly now, we're going to look at some logarithmic equations. Just at the bottom of page 7, we have a little bit here to solve log equations. We can consider the interaction of the exponent with the base as a way to manipulate the equation. We may have to apply properties of logs, which you guys are all experts on by now, to find ways to rewrite these equations. So if we turn over to page 8, we have 4 examples that we're going to look at. Let's see how they look, and we'll see what we can do with them. All right, so this is my favorite type of problem to approach with logarithms, and all we are going to do is we are going to rewrite as an exponential. What does that mean? Well, this 3 here will become the base. This 3 becomes the exponent. You know what? Let me color code those differently so you can see which is which. Now, what we're doing effectively is we're saying 3 to the third equals 3 to the log base 3 of x minus 4. But if we kind of cut through that step, what we're left with is 3 to the third equals x minus 4, and that's something we could solve very easily. We know 3 to the third is 27, so x will equal 31. So we rewrite as an exponential, or use a base to eliminate the logarithm. All right, let's try example B. Again here, I like to immediately rewrite this as an exponential. Right? We know that even though there's no base indicated, we know that this is saying 10 to the 0 power equals 2x. And now that's a really simple equation. We know that anything to the 0 power is 1. So if 1 equals 2x, we know that x must equal 1/2. All right, team, we're almost there. We got two more examples to look at. So here we have a situation where we have multiple logs, right? The first two, we had a single log in each expression. Here, if we have multiple logs, we want to start by condensing and then set arguments equal. And then again, we will check for a extraneous solution. So what I'm going to do, I'm going to write this as log of 8, nothing changes on the left. And on the right, I'm going to condense these to a single logarithm. Because those logs are being added, I can multiply those arguments. And if I have the log of something on one side and it equals the log of something else, I can just make those quantities equal to each other. Well, now we have a quadratic. So we will set it equal to 0 to solve. This one is factorable. And we get two potential solutions, 4 and negative 2. But again, red flag time, right? Make sure you're paying attention. We always need to check for extraneous solutions. An extraneous solution is a solution to a related equation that we've created, but one that does not fit in the domain of our original problem. So we created a quadratic here. This quadratic has two solutions, one positive and one negative. But what we know about the domain of logarithms is that we can never take the logarithm of a negative number. So if we were to plug in negative 2 either in for x or in for x minus 2, we would be taking the log of those negative numbers. This will create a domain error. In other words, negative 2 must be excluded from our solution set. It is extraneous, and 4 is our only legitimate solution. All right, one last problem here. Let's see what we have. Here, it always gets confusing, right, when we have E showing up, especially we have E on both sides of the equation. There's two approaches here, and I think the one that makes the most sense is to just do what we did on the last problem. We are taking the natural log of two different values, so E must be the same as the square root of x minus 4. Well, I know that if I were to add 4 to both sides, and then square both sides, x will equal the quantity e plus 4 squared. And there's our answer. So we can leave it in those terms. If we wanted to plug in e plus 4 and then square it, we could get a numerical value. This might come down to, is this a calc or non-calc problem? In this case, if it were non-calc, we would stop here, e plus 4 quantity squared. And if it were a calc problem, we could plug in to find that x actually equals 45.135. Thanks for hanging in there. Good work. And next video will be all about graphing.